everybody. In this video, we're going to go over test number 4, which was on Unit 4 on transformations. So the first question is asking us for the image of point A under a rotation of 90 degrees. So remember, when they don't specify where we're centered, it means that we're centered at the origin. So this is a rotation centered at the origin. And when the direction isn't specified, it's assumed that we're rotating counterclockwise. So we're rotating 90 degrees counterclockwise around the origin. So we have a rule for that. So our rule for rotations 90 degrees counterclockwise about the origin is that we take our original point, and our original point, the x and y coordinates switch spots, and also the original y coordinate becomes negative. So here you can see what that looks like. The x and y coordinates switch spots, and the original y coordinate becomes negative. That means the sign switches. If it's positive, it becomes negative. If it's negative, it becomes positive. So the point we have here is 5, 2. So the original y coordinate is 2, so that's going to become negative 2. And the order of the x and y coordinates is going to change. So that is choice 4, negative 2, 5. Question number 2 says, which point shown in the graph below is the image of point P, after a counterclockwise rotation of 90 degrees about the origin? So a lot of people pick B. So B wouldn't be a rotation. Notice how P and B are mirror images across the x-axis. They're both equal distance from the x-axis. So remember, mirror images is a reflection. So point B is actually point P after a reflection over the x-axis. So the choice that we're looking for here is choice number A. We're rotating 90 degrees. Once again, it tells us direction counterclockwise, so we're going in this direction, not this direction, so don't be confused by the direction. If we estimate and say that this point P is the point, let's say 6, negative 2, I'm just estimating here, I don't know exactly what it is, then based on our rules of rotation for 90 degrees counterclockwise about the origin, the rotated point, P prime, would be 2, 6, and that would put that about right over here. So that's just like an estimate using an approximate point for point P, where the rotation would approximately end up. It would be approximately where point A is. Okay, moving on. For number 3, it says we have a function, and if f is reflected in the line y equals x, what point will be in? So we're going to do this 2 ways. We're going to do this with the rules of reflections, and then we'll also do it graphically. So first, with the rules of reflection, our rule for reflecting over the line y equals x is that you simply just switch the order of the x and y coordinate. So our function set after the reflection would consist of the point 3, 2, the point 7, 4, and the point 5, negative 1. So that tells me that the correct answer choice is choice number 1. That's the only choice that's actually in the set of the function. We can also do this graphically. I'm just going to take a second and graph my points on a grid. So all I did is take the 3 points that were given to us in the function set, the original function set, and I just graphed them. And we're going to be reflecting them over the line y equals x. So the line y equals x has a y-intercept of 0 and a slope of 1. So I'm just going to get a few points that are on the graph, and then I'll connect it together with a line. But this is just a reminder of what the line y equals x looks like. It's a diagonal line, slanted, slope of 1, passes through the origin. Its y-intercept is the origin. Okay, now I'm going to just connect together. Let me just make sure I have a line. There we go. And that's all connected together there as best as I can. Wonderful. Okay. So now we're actually going to reflect over this line. So let's do it. So from this point, we have 1.5 diagonal boxes to the line y equals x. So I'm going to move another one diagonal boxes till I get to the image of that point reflected over the line y equals x. This point here is half a diagonal box from the line y equals x, so I'm going to move another half of a diagonal box to reflect it. Same thing here. I'm going to count 1, 2, 3 diagonal boxes. So I'm going to move 1, 2, 3 diagonal boxes. And if I list the points here really quickly, 1, 2, 3, this is 3, 2. 1, 2, 3, 4, 5, -1. And this is 4, 5, 6, 7. 1, 2, 3, 4. And that's 7, 4. And notice that these are the same 3 points that we got super quickly before by using our rules for reflections. So we see that 5, -1 is the correct answer choice, again, graphically. Doesn't matter if you do reflections graphically or algebraically. I actually recommend doing them graphically, so that way you don't have to worry about memorizing all of the rules for reflections. Rotations, it's pretty good if you do know the rules. So I would recommend, especially before the Regents exam, that you make sure that you do know those rules for rotations. You'll be able to do any rotation question. Triangle ABC has 3 vertices. And under a translation, A prime is located at 4, 4. And we need to find point C under the same translation. So from point A, which is, let me use my pen here, which is at the point 1, 3, to point A prime, which is at the point 4, 4, let's see what happened. So for our x coordinates, we added 3 to get from 1 to 4. And for our y coordinates, we added 1. So this is a translation of 3, 1. Add 3 to the x coordinates, add 1 to the y coordinates. So we're just going to apply that same translation to point C. Point C starts off as the point 4, 0. We want to figure out what C prime is. Well, if I do the same thing, if I plus 3 to the x coordinates and I plus 1 to the y coordinates, I get 7, 1. And that's answer choice 1. In which quadrant would the image of point 5, -3 fall after a dilation using a scale factor of -3? So remember, if it's not specified what the center of dilation is, we do assume that the center of dilation is at the origin, which means that we can use our rule to dilate by our scale factor of -3. All we need to do is multiply the x and the y coordinate by -3. So that tells us that our dilated point would be the point -15, 9. So here we have our coordinate grid, our coordinate plane. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Remember, in math, we always assume that we're going counterclockwise in the counterclockwise direction for like a rotation. If it's not specified, because that's the way that the quadrants go. The quadrants go in a counterclockwise order. So 1, 2, 3, 4, the quadrants go in a counterclockwise order. So the point 5, -3 would be 5 would be over here, -3 would be somewhere down here. That would be in quadrant number 4. Finally, triangle A prime, B prime, C prime is the image of triangle ABC under a dilation such that A prime, B prime, so a new line segment on the triangle, is 3 times the line segment on the original triangle. So let me take a look at this by making a picture. So let's say this is before the dilation and after the dilation. I see that the dilation is greater than 1. It's making bigger because the image line segment is triple the original line segment. So we are getting bigger here. So I'll call this ABC, and I'll call this A prime, B prime, C prime. Well, if I just make up numbers, if I say like this was 3, well, then this one's 9, according to what they tell us. If like this one was 2, then this one's 4. If this one was 5, 2. Sorry, that one's 6. I can't multiply today. Okay, and if this one's 5, this one's 15. So obviously these are not congruent. They're not exactly the same. We're taking one and we're making it 3 times bigger to get the other, so they're not the same size, but they are similar because they are proportional by the same scale factor of 3. So the answer here would be similar, but not congruent. Okay. A triangle is dilated by a scale factor of 3 with the center of dilation at the origin. Which statement is true? So that's kind of like the one we were just looking at. But this one's asking about area, it's asking about perimeter, slope, and angle measurement. So I'm going to start with the bottom one, number 4. That one says the measure of each angle in the image is 3 times the measure of the corresponding angle of the original triangle. Well, we know that that can't be true because remember when we talked about proving triangles similar to each other, we talked about how angle was a way of proving triangles similar, which meant that 2 corresponding angles in the 2 similar triangles were congruent. And if 2 angles are congruent to each other in a triangle, then that means the third corresponding angles have to be congruent as well. They have no choice because all the angles in the triangle need to add to 180. So this is not true. And we have similar triangles, which we do have anytime we dilate a shape, it produces similar figures. If we have similar triangles, their corresponding angles are congruent. So the angle measures of the corresponding angles would be the same. Dilations preserve angle measurement. In fact, all of the transformations preserve angle measurement. Okay, number 3. The slope of any side of the image is 3 times the slope of the corresponding side of the original triangle. Might be true. Let's go to that one as a last resort. We can test that one out on a grid, but if we don't have to, I'd rather not. So let's go to 2 and 1 and see if we can find a true statement there. Oh, wait, number 3, we actually don't have to. We can rule that one out as well. Because remember, we had a whole discussion in class about how dilations preserve parallelism. We talked about that if we have a line and we dilate the line, the image line will have the same slope because dilations preserve parallelism. So the slopes of corresponding sides would be the same if we have similar triangles. Dilations preserve parallelism. So that's an easy one to eliminate. That's not true. Okay. Number 2. The perimeter of the image is 9 times the perimeter of the original triangle. Let's test it out. Let's say this is 1, this is 3. Let's say this is 2, that's 6. And let's say this is 3, that's 9. Perimeters, add them up, 3, 5, 6. The perimeter of this one would be 6. 9, 10, 11, 12, 13, 14, 15, 18. So it looks like the perimeter is only 3 times. So it's not 9 times, so that's not true. Okay. Maybe area. Let's talk about area. Just to make it simpler, for the area example, let me talk about right triangles, which can be similar to each other as well. So that way we don't have to worry about finding heights or using Pythagorean theorem or any of that stuff. Okay, so I'm going to start off with a 3, 4, 5 triangle, which I know is a right triangle. It satisfies the Pythagorean theorem. So then this would be 9, this would be 12, and this would be 15. So if I found the area of this triangle, that would be 1/2 base times height. So that's half of 12, so that's 6. And if I found the area of this triangle, it would be 1/2 base times height. So that's 1/2 of 9 times 12. The big number, let me do that on my calculator. 9 times 12 is 108. Half of that is 54. And 54 divided by 6 is 9. So that's true. The area is not 3 times as big as the original. The area is 9 times as big as the original. 6 times 9 is 54. So we found that answer choice 1 was the correct answer. number 8. What we need to do for number 8 is we need to reflect over the line y equals x, and then we need to dilate by a scale factor of 2. So really easily, using the rules of reflections and dilation centered at the origin, to reflect over the line y equals x, all we need to do is switch the order of the points. And then for dilation centered at the origin, we could just multiply x and y by the scale factor. So that would be 14, -4 when we multiply x and y by 2. So that's answer choice number 4. We can also do that graphically. We will do it graphically so you can see how that. So I just plotted in red the point -27. That's our point that we're starting off with. And I have from before our line y equals x plotted. So we're going to do the same thing as before, and we're going to reflect over the line y equals x first. So I'm going to count the boxes: 1, 2, 3, 4, 4.5 diagonal spaces from the dot to the line. Oops, another half. 1, 2, 3, 4. So that's another 4.5 diagonal spaces over the line. So this is the image of the original red point after we reflected over the line y equals x. Now we need to dilate by a scale factor of 2 centered at the origin. So what I want to do first is I want to see how far this point is away from the origin, and then I'm going to double that distance. The thing is, it's going to come off of my graph, but I can tell you what you would do if you did have a bigger graph. So counting from the origin to this point, I have 1, 2, 3, 4, 5, 6, 7 to the right and 2 down. So I'm going to write that 7 to the right and 2 down. So what I would do now is I would move another 1, 2, 3, 4, 5, 6, 7 to the right and 2 down. Unfortunately here my graph isn't big enough, but where you end up, that would be the image of the point after the dilation. So then we would have both reflected and dilated the point. So you can see here, it's especially useful to use the rules of transformations, especially dilations here, since it does make something bigger and our grids are not super huge. So that way you don't have to worry about the amount of space you have on the grid. But you can always redo your grid so you have more space in whatever direction you need. You can redraw your X and Y axis. Okay, let's see if there's anything else here. Yes. Okay, so what we need to do is describe a sequence of similarity transformations that shows triangle XYZ is similar to triangle UVZ. So for this one, there wasn't like one correct way of wording it, but what you did need to do is describe a sequence of transformations. So that means more than one. So people who just wrote like rotation, that's really not going to work here. Sequence means more than one. So if you just wrote one, you definitely got points off. And when it says you need a sequence that shows the two triangles are similar, immediately dilation should come to your mind because dilation changes size and makes things similar to each other. So I know that a dilation is going to be included here. So rotation followed by a dilation would probably be the best option here. You need to rotate this triangle so that it's facing the same way as the bigger one. So we're going to take it and we're going to rotate it until it's overlapping with this triangle over here. So we can write that, we can word that, we can say rotation centered at point Z. We want to center it at point Z because it's already attached to the other triangle at that point. So we can just spin it or rotate it, turn it around that point to make it overlap. So we want our rotation center that point Z. And then we can write something so that angle X is congruent to angle U, and angle XZY matches up to angle UZY V. Now, I'm just using the wording in the question here of the corresponding angles that need to match up to each other, because our goal of rotating it about point Z is to make the corresponding parts match up to each other so that the two triangles overlap and are oriented in the same direction. And then we are going to dilate it, once again, center at point Z, because at this point, the two triangles will be facing, this triangle will have turned so that it's facing the same direction as this one. It's probably just going to be a little bit smaller, but you know, it's going to be facing the same way. So we can say center that point C so that the corresponding parts match up. So let me rewrite this a little bit clearer way because it's a bit convoluted. So let me rewrite that. So I just rewrote what I was saying before in a less convoluted way. I paused the video to rewrite it. So I just cleaned up my writing a bit. So rotation centered at point Z, and we're going to turn it until this top piece of this triangle matches up with this top piece of this triangle. So until angle XZY matches up with angle UZV. Once we rotate it and turn it that way, I can also specify either clockwise or counterclockwise. It wouldn't matter, both directions would get us where we need to go. So once we do the rotation, our image triangle would look something like the blue one I outlined here. It would be facing in the same direction. It would be oriented in the same direction. It'd be lined up to the bigger triangle, but it wouldn't be the same size. So then we would have to dilate it, once again, centered at point Z, because that's the point that they would be attached by, so that the other corresponding parts match up to each other. And I just wrote so that angle X and angle U match up to each other. So angle X and angle U match up to each other here and here. That would make sure that they are the right size. You can also write so that the other corresponding parts match up to each other as well. So I do want to also clarify, you might have lost points if you didn't put a center of dilation or a center of rotation. Some people did lose points for that. Also, it depends on how you described it, but if you said reflect over point Z, that and then dilate, that actually wouldn't be correct, because if I reflect over point Z, I just want to show you guys, it would be over here, the image triangle. And then if you make it bigger, like, yeah, it would get bigger, but it would still be over here, not over here. So some people did describe a reflection in a way that would make it match up. But if you just said reflect over point Z or line Z and then dilate, that wouldn't work because you wouldn't end up with it exactly overlapping. So be careful with that. The best option here is a rotation followed by a dilation. I think that's the most direct way here. Okay, next one, really, really simple. Nonagon. So we have 360 over 9, and that's 40 degrees. Okay. For the next one, we need to translate each of the points and then reflect them. So I'm just going to do it graphically. So let me pause the video so I can graph them. So first we're going to be translating, because remember, what comes here goes first when we're talking about transformations. So first we're going to be translating each of the points 7 units to the right and 5 units up. So I'm going to move 1, 2, 3, 4, 5, 6, 7 to the right. 1, 2, 3, 4, 5. That would be right here. Oh no, what happened there? I'm going to have to count again. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And that is A prime. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And that is M prime. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That is T prime. And then finally 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That is H prime. So we just did the translation. And then the only other thing that we have left to do is the reflection. Let me just join these points together real quick. There we go. Enough. And now let's do the reflection over the x-axis. So the x-axis is right over here. So I'll start here with point A, 1, 2, 1, 2. So that would be A double prime. 1, 2, 3, 4. 1, 2, 3, 4. That would be T double prime. 1, 2, 3, 4. 1, 2, 3, 4. That would be H double prime. 1, 2, 1, 2. That would be M double prime. Let me connect those together, and then I'm going to write down the points. A lot of people lost points because the question does say to state and label the coordinates of quadrilateral math double prime. So if you didn't state and label like I'm about to do, you did receive points off. So M double prime is 1, -2. A double prime is 1, 2, 3, 4, 5, 6, -2. T double prime is 1, 2, 3, 4, 5. 1, 2, 3, 4. 5, -4. And H double prime is 1, 2, 3. 1, 2, 3, 4. 3, -4. And there we have it. Let's move it forward. Part B, are the pre-image and image after the sequence of transformations congruent to each other? Yes, because reflections are rigid motions, meaning they preserve side lengths and angle measures. Remember what makes two triangles or two shapes congruent to each other is that they have congruent corresponding sides and congruent corresponding angles. So in order to be sure that the pre-image and the image are congruent, we need to mention that the side lengths stay the same and that the angle measurements stay the same. And that is what is meant by saying that this transformation is a rigid motion. Okay, now we have the constructions. So for the constructions, I'm going to get started here by just connecting two corresponding pre-image and image points. And this one doesn't work out perfectly. It really doesn't. It was an error with the question. So as long as you followed the steps and you did all the steps correctly, even though your line of reflection is not going to end up perfect, I did give the full credit for that. That was an error with the question. So I'm going to open up to more than halfway down the line segment. The exact distance doesn't matter, just more than halfway. And I'm going to make my arc above and below. Then without changing my compass, I'm going to just move over to the other endpoint. And I'm just going to make the same arc above and below. And let me just dot those intersection points so I can see those clearly when I come back to it. Okay. Now I am going to just switch my compass color. I'm going to pick up my compass and I'm going to move to the other line segment where I joined the pre-image and the image points. I'm going to open up, once again, the exact length doesn't matter, just more than halfway. And I'm just going to make an arc above and below. Then without changing anything on my compass, I'm going to turn it around. go over to the other endpoint, and make the same arc above and below. And notice that the intersection points don't match up with each other. So we're going to try as best as possible to make a line through as best as possible. It's not perfect. Mine ended up being pretty decent, but it's not perfect. There we go. That would be our line of reflection. And as some of you pointed out in the test, it doesn't work out perfectly. It does not. On the Regents exam, whatever they give you, if you have to construct a line of reflection, will work out to be going right through all the intersection points. But it's pretty close. When I did it now, it's pretty close. When I did it on paper, it was a little bit more off, but now on the computer, it's a little bit closer. Okay, we need to dilate by a scale factor of 3. So I saw other people making the triangle smaller. We are not dilating by a scale factor of 1/3 or 1/2. We are making it bigger. We're dilating by a scale factor of 3. So what you should expect to see is that your new triangle afterwards should be triple the size of the one that we see here now. So if it got smaller and not bigger, then it should be like, hey, I probably did something wrong here. So remember that the center of dilation, the image point, and the corresponding pre-image point and the corresponding image point should all lay on the same line. I don't know where exactly the image point is going to lay, so I'm just going to make this line pretty large. That way I can find where it's going to end up. What I'm going to do is just get my compass, and all I want to do is measure the distance. And let me turn my compass around. There we go. I just want to measure the distance from the center of dilation. Oops, my compass keeps moving. So I want to measure the distance from my center of dilation to my pre-image point, so to point X. I'm going to try to get this as good as possible. There we go. And I'm going to just make an arc to show that I measured. Not perfect, trying to be as close as I possibly can though. Okay, then I'm just going to copy that distance. So that would be double the distance. So that would be a dilation of 2. But I want a dilation of 3. So I'm just going to triple that distance. And this is going to be where the image of point X, so we can label that X prime, will be after a dilation with a scale factor of 3. We're just going to do the same exact thing for the other points. So once again, drawing a line that connects the center of dilation to the pre-image point, and I'm leaving space because I don't know where the image point's going to end up along this line, but I do know that they will all 3 be on the same line. Let me change my color so I could be using a different color. I'm going to grab my compass, and I want to put my compass to measure the distance from the center of dilation, so from point A, to my pre-image point, to point Z. Let me try to get this as good as I can. There we go. I'm going to make an arc to show I measured that distance. Then I'm going to just copy that distance and make another arc. So I just doubled the distance. So that would be a scale factor of 2. But I want a scale factor of 3. So I'm going to do it again. And that's a scale factor of 3. So that would be the point Z prime, the image of point Z after a dilation with a scale factor of 3. And notice that Z prime is triple the distance from point A as point Z originally was. That makes sense. And remember, we should expect our ending triangle to be 3 times as large as the triangle we started with. That's another way we can check if we're doing this right. Last but not least, point Y. We're going to dilate that one. So once again, going to connect the center, the pre-image point, and the image point will be somewhere on that same line. Let me get a new color. I'm going to take my compass and measure the distance from the center of dilation to the pre-image point. So I want to measure to point Y. Okay, that looks about good. Okay, once again, we're not going to be 100% perfect, but we try to be as accurate as possible. Okay, let me copy that distance. Oops, trying to get it almost exactly on that point. There we go. And we want a scale factor of 3. So we just have to copy that distance one more time. There we go. that would be the image of point y after a dilation with a scale factor of 3. Notice how point y prime is 3 times the distance from point A as point y was. And what's really also going to make it super clear if we did the right thing is now when I connect all of the new image points together, the new triangle should be triple the size of the original. Oops. And look, my purple triangle is definitely bigger than my original black triangle. It's triple the size.